Good morning, everyone. My co-author in this work is Dr. Sean Rogers, and what I'm going to talk about today is some work that was done a number of years ago, but I think it's still relevant regarding magnetically loaded AMC antennas. The outline goes as follows. I'll go through a brief motivation, which I'm sure many people in this room are already familiar with. I'll discuss the design of an AMC surface, and what's new here is the magnetic material development and how it's integrated in with that surface. I'll describe some antennas that were fabricated and the experimental results that came out of that work, and then some brief conclusions. Okay, well, the motivation is simply the need for low-profile antennas in both commercial systems and military systems. And the idea is simply to make an antenna system that's as thin as possible for form factor reasons. One of the motivations for this work was also to address cell bands. We wanted to see if we could produce AMC antennas that would cover multiple low-band cell bands, basically the 860 and 900 bands for GSM. And so that was another motivation for this work. Okay. In terms of what is an AMC, well, I'm sure many of you are familiar with the idea of a corrugated metal slab. It was one of the first concepts where you could create a lossless reactive surface where it inhibited the flow of currents in a given direction as a soft surface, for instance. Modern versions include printed circuit technology, i.e. the Sieben-Piper high impedance surface, or what we used to call the Sieben-Piper AMC, and it's still known as that, I believe. And what is new about this work is that we're replacing the dielectric spacer that encompasses the vias with a magnetodielectric material. And the material is going to be the elastomeric material that is alluded to in the title. An AMC surface has two fundamental properties which make it useful as an antenna. The first property is that it's a high impedance surface. So you have a resonance whereby the tangential E to tangential H is high, and that provides the correct phase for the image so that you can get radiation. And the second property that you want to create is one whereby a surface wave band gap exists, where the TM mode is cut off. The TE mode is also cut off as a guided mode, but a TE mode is allowed to propagate as a leaky wave. And so the idea is to operate within the band gap where the leaky wave occurs. And both of these properties really have to coexist in frequency to make an effective AMC antenna. The reflection phase of the antenna is an important consideration. And here, these diagrams show that if a plane wave is incident on the front face of an AMC structure, the structure really behaves as an impedance matching system, where a short is reflected into an open at the surface. And the phase angle as a function of frequency crosses through zero. You have a resonance condition that occurs there. And then there's a bandwidth associated with the plus and minus 90-degree reflection phase. That bandwidth can be expressed analytically as 2 pi times the permeability of the host medium that contains the vias times the normalized height, d over lambda, where d is the physical thickness of that media. Okay. So the point here is the bandwidth increases with magnetic permeability. If we can increase the permeability, then we can increase the operational bandwidth of the antenna. In these experiments, the AMC structures are constructed as follows. The back plane is comprised of a foil on one side of an FR4 layer, in this case a 14 mil thick FR4. And on top of that, we laminated an elastomeric material that is 100 mils thick, and I'll get into that description here shortly. And then we laminated a layer of Rogers 4003 that was 8 mils thick that had patches offset on both sides. So this is the capacitive FSS. And then later, the via holes were literally drilled through the entire structure because although the FSS on top had plated through holes, the isoprene layer did not. So we drilled through it, and then all the views were inserted by hand. Okay. The AMC structure was actually designed with the help of some simple tools, namely this is a circuit simulator that was employed. The bottom here is an equivalent circuit. On the top here we see some optimization limits. What we were doing here is optimizing the phase such that we get a reflection phase around 900 megahertz under the constraints that we were limited to these two transmission lines modeling the two layers that have a known permittivity and a known thickness. And what we were optimizing was the capacitance that loads the top of the structure, namely the FSS. And we can control that capacitance by the physical size of the patches, as well as their period. Okay, and in this case, the optimization turned out to be about a 2.3 picofarads per square for that top FSS. Now, the magnetic material that we employed is a combination of two things. One is a gum rubber material that's basically a binder, and the second is an iron powder, in this case obtained from BASF, and it's their type HQ iron powder. These are iron oxide particles, and they have a mean diameter of about 1 to 2 microns. We had two different types of materials fabricated with a kneading process. Basically, the powder was mixed in with the gum rubber, and we had two different cases fabricated, a 40% loading by weight and a 50% loading by weight. Both were tried in the antenna substrates and measured. The measurements on just the material parameters of the loaded HQ isoprene are shown here. This is for a 40% loading by weight. The permeability, relative permeability, is approximately 3.5 at a frequency of around 900 megahertz, which is where the AMC was designed. And the magnetic loss tangent is about 1/10, or 0.11 at that frequency. If you take the ratios, that's what it comes out to be. The permittivity is constant, as you would expect, about 8.5 in this particular case. And then the more densely loaded magnetic material had a higher relative permeability of about 4.6 at 900 megahertz, but it also had a higher magnetic loss tangent, as you would expect. And a slightly higher relative permittivity of around 11. Okay. And these tests were done using an airline, coaxial airline. The antenna experiments were, I can outline it here as follows. All the antennas had the same footprint, same physical size. They were about 2.125 by about 4.25 inches. So in terms of a wavelength at, say, 860 megahertz, it's about 0.15 wavelength. I'm sorry, I guess it's not shown here, but it's about 0.16 wavelength by about 0.32 wavelengths. So these are fairly small footprint AMCs. They were intentionally designed to be small because we had some motivation not only to think about what was possible to fit into a cell phone at the time. Now this was done a number of years ago, back in the year 2000 when it was designed. And we also had at the time interest in potential RFID reader antennas. So the bands that this operates at would fit there as well. But we designed several antennas with the 40 and 50% loading of magnetic material. And the 40% case had a without via example. We wanted to know what happens if we just get rid of the vias, because they're the most laborious part of all this. And we predicted that we would have issues, and we did. And what was measured out of all this was the return loss deficiency in the gain patterns. Okay. Here's an example of one of the longer wire antennas. There was two different lengths of bent wire monopoles that were employed, a 2.0 inch and a 3.3 inch case. The bent wire monopole